up our first chapter on acids and bases, we're going to talk about the acid-base properties of all different kinds of salts. So salt, just in case you forgot, is another name for an ionic compound. And when a salt dissolves in water, we assume that it breaks up into its ion and will move about independently to do whatever it needs to. So under certain conditions, these ions can behave as acids or bases. Salts that produce neutral solutions consist of cations of the strong bases and the anions of strong acids. And so then they have no effect on the H plus dissolved in the water. And this is because they completely dissociate, as we mentioned earlier this chapter. So possible solutions that could be neutral include potassium chloride, sodium nitrate, and potassium nitrate. So for example, to know why these are evening out, when we split them up and make them into an acid and a base, like for example the potassium chloride, the potassium will go with hydroxide and the chloride will go with hydrogen, so we make potassium hydroxide and hydrochloric acid. Strong base, strong acid, neutralize each other. Or for example, for the sodium nitrate, we have sodium goes with hydroxide and the nitrate goes up with the H, so then strong and strong. Strong base is sodium hydroxide and strong acid is nitric acid. So they even each other out. Salts that produce basic solutions we have when the cation has neutral properties, so such that's making a strong base when it pairs up with the hydroxide, and whose anion is the conjugate base of a weak acid. So then the solution can be basic. So the Kb is equal to the Kw over the Ka. When a strong acid is dissociated in water, the anion can appear to be a strong base, and so this happens when the ion competes with H2O and the OH for the H+. So we have our strong base being in there from when it dissolved, and we have the strong conjugate base as well, making this a basic solution. So the relative strengths for each of these species: the hydroxide is the strongest because that has to do with the strong base, and then the conjugate acid is next strongest, and then the least strong would be the water that's all competing for the H+. So we're going to use this information to help us figure out the pH of the solution when we dissolve sodium fluoride. And so in this solution we have the species the Na, the F ion, and water. Okay. Well, the Na is going to make a strong acid or strong base, but the F is going to pair up with the weak acid to make, or with the H to make the weak acid, hydrochloric acid. So we are going to use the F to help us figure this out because we have the molarity of the overall solution. So we're going to have our basic equation for the dissociation to make a hydroxide. So our products will be HF plus hydroxide. Okay, and so then we can write our Kb expression from that. So Kb, don't include water, remember that, will be the HF concentration times the OH concentration all over the F minus concentration. Okay, so to fill in our ice chart, we are starting with a 0.3 molar solution of NaF, so that 0.3 is going to go with the F minus, and that's because there's only one F in that formula, so we know that that's 1 to 1. Then we have 0 for the products. Our change, subtract, add to the product side, like we've been doing, and so at equilibrium it'll be 0.3 minus X, and X, and X. Well, before we plug into our Kb expression, we can't really do much because we don't have a Kb. We have a Ka instead. And so what we can do is use that equation that was just a little bit ago, where Kb is equal to the Kw divided by the Ka. So to find the Kb, we can take 1.0 times 10 to the negative 14 and divide that by our Ka, the 7.2 times 10 to the negative 4. Well, when you divide, you get Kb to equal 1.4 times 10 to the negative 11. All right, so then let's go ahead and set up our KB expression, plugging in our new KB. So we have 1.4 times 10 to the negative 11 equals, and it's going to be x times x on top, so x squared, over, KB is pretty small, so let's do our assumption. Just leave off the minus x and put the 0.3 instead. When you do all of this, then you solve for x, and x is equal to 2.0 times 10 to the negative 6 molar. And so x, this value, is for our HF concentration and for our OH concentration. And since it's equal to the OH concentration, we now can use this number to help us figure out the pH. I hope you left yourself some room. So if we know that the OH concentration is our 2.0 times 10 to the negative 6 molar, then our first negative log of that number will give us the POH. So the POH is equal to 5.69. Well, that's not our final answer because we need the pH. So we have to subtract from 14 to get that. And our pH final answer is 8.31. And this kind of checks out because 8 is greater than 7, so that's telling us it is, in fact, a basic solution. If we have salts that produce acidic solutions, this means that the anion is not a base, and so then the cation is the conjugate acid of a weak base, and it produces an acidic solution. So for example, when ammonium chloride dissociates, we have this equation creating the H+, and if you need an example on how to do the math with these problems, it's very, 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 very similar to what we just did with example 13. But there is an example on page 689 in your textbook for that, if you need to look at it. Another type of salt that produces an acidic solution is one that contains a highly charged metal ion. So for example, when aluminum chloride is dissolved, it creates a solution that is significantly acidic. But the aluminum ion is not a Bronsted-Lowry acid. But the hydrated ion that forms when it has 6 waters, that's why it says H2O6, are attached onto that ion. And so when that happens, then it can lose an H to become acidic. The high charge on the metal ion polarizes the OH bonds in the attached water molecules, making the hydrogens in these water molecules more acidic than those in free water molecules. So typically, the higher the charge on the metal ion, the stronger the acidity of the hydrated ion. So, just so we all know, like a high charge would be 3, and then that would be greater in acidity than 2, and that would be even greater than 1. So it goes backwards like that. So the higher the charge, the stronger the acid. So that means the closer to 1 the pH would be. So if you have a salt that affects the pH of the solution, where both ions do it, not just one, which we've considered so far, then it gets a little bit more complicated. But to help us ourselves out, we're just going to think about it qualitatively instead. So we will just have to compare the Ka and the Kb to tell whether it's acidic, basic, or neutral. So just remember, if pH is less than 7, it's acidic, pH greater than 7, basic, and equal to 7, neutral. And the farther on the outskirts of that range you get, the stronger it is. The closer to neutral it is, the weaker it is. So for example 14, we're just going to qualitatively look at these and decide if it's acidic, basic, or neutral. And so we need Ka and Kb's for that. So for the first one, we have ammonium acetate. And I looked up in a table, which there's many different tables in your textbook that gives you this information. I used the appendices for these, which are on pages A22 to A23. And there's a bunch of Ka information there for you. But the Ka of the ammonium is 5.6 times 10 to the negative 10. Okay, and then for the acetate ion, I had to look at acetic acid, but that Ka was 1.8 times 10 to the negative 5. Okay, well, I need to compare a Ka to a Kb. So I decided, okay, the second one, let's go ahead and use our equation that we saw before, Kb equals Kw over Ka, to find the Ka, or the Kb, excuse me. So then I found that the Kb is equal to 5.6 times 10 to the negative 10. So with the comparison, Ka is equal to Kb. So that means that it's a neutral solution because they even each other out. For the next one, we have ammonium cyanide. Ammonium, we just used the Ka, so you can just copy that down again. The Ka was 5.6 times 10 to the negative 10. But this time for cyanide, I had to look at hydrocyanic acid to find that the Ka of that was 6.2 times 10 to the negative 10. So using our whole Kb equals Kw over Ka, I found that the Kb of the solution is 1.6 times 10 to the negative 5. So for this one, if we have times 10 to the negative 10 versus times 10 to the negative 5, negative 5 is bigger. So Kb is greater than Ka, so this is a basic solution. And last but not least, we have our aluminum sulfate. And this is the one that contains that hydrated ion, the cation. So our first ion in the solution would be the AlH2O plus 3. And then the other ion would be the sulfate ion. Alright, so then the Ka, which I had to find in a different table, so don't worry, I won't make you go find it somewhere else, is 1.4 times 10 to the negative 5 for the hydrated cation. And then for the SO4, looking at the tables, I used the Ka2 because that's how you make up, using Ka2, the sulfate from sulfuric acid. And that Ka2 is 1.2 times 10 to the negative 2. Then we had to do our Kb equals Kw over Ka to find that the Kb of the second is 8.3 times 10 to the negative 13. So for this one, Ka is significantly bigger than Kb, so that means that it is in fact acidic solution. So the effective structure on acid-base properties. Any molecule that contains a hydrogen atom has the potential to be an acid, but many such molecules show no acidic properties. This depends on the strength of the remember what is holding the whole molecule together, intramolecular bonds. The stronger the bond strength according to electronegativity, the weaker the resulting acidic solution. So here are two tables that give you a variety of information. Look how in table 14.7, first off, there's the bond strengths listed there, and then the acidity in water. So actually, if you look, the weaker you go down the line for the bond strength, the stronger you get. Also, HF is the only one listed there that is a weak acid, versus the other three are all strong acids. And then up above is different types of salts, examples of each of them, and how it can act in solution and what the pH would be. There is more information in your textbook through pages 692 to 697 about things called oxyacids, acid-base, Lewis acid-base properties of oxides, Lewis acid-base model, and problem-solving strategies for you. Lewis acid-base model, that is not an AP standard, so we are not going to take the time for that. But other stuff there could be interesting if you want to check it out. So this ends chapter 14, and we have 3 homework problems this time, numbers 114, 117, and 120.